Hi everyone, so in today's video we're going to have a look at polymers for the A-level product design exam contents. This is an updated version, so if you're on the YouTube channel you'll find a video from last year, but this one's been tweaked slightly to have a little bit more updated information on it. So what you need to know for the exam is basically identify the 4 different groups of polymers and their properties, be able to give different examples of polymers in each group and what they could be used for, what additives are and how they can be used, and then what the different symbols you can find in the recycling table mean as well. So the first thing, now if you're watching these in order and you've seen the metals video first, these next couple of slides are exactly the same. But essentially, like with any material that you use, in an exam you can't just say it's made out of plastic, it's made out of metal, it's made out of wood, because that is a very, very generic thing. You need to be a lot more specific in why that specific material has been chosen, and the main reason why those specific ones have been chosen are down to those properties that that material has. So, two plastics can have completely different properties. One will be useful in one instance, one will be completely useless. So one's got an incredibly high melting point, one's got quite a low melting point. So if you try and make that be an electrical socket or near a heat source of any kind, it would just melt straight away. Whereas if you had one with quite a high melting point, it would be ideal. So it's understanding that essentially whatever the thing you're going to make, whether it's a product or whatever it may be, furniture, um, you need to figure out what properties does it need. Does it need to be able to withstand extreme heat? Does it need to be able to withstand being outside for long periods of time? Does it need to withstand general wear and tear? Once you know what properties you need, then you can sort of reverse engineer and see which materials suit the need that you have. So what you have is, with properties, they're typically broken down into mechanical and physical. So mechanical are the ones that how a material reacts to an external thing happening to it, an external force happening to it. Whereas physical properties are the actual makeup of the structure of the material and how things can flow or pass through them. So just to help clarify that a little bit, so mechanical properties, so these can be things like compressive strength, so the ability to like withstand like pushing or crushing. So an example of that might be, say, like the legs of a chair or something like that. So the compressive strength being the weight that when you sit on it, it needs to be able to withstand. If it didn't have good compressive strength, you would sit on it and then you'd fall back and hurt yourself. Tensile strength being able to withstand pulling forces. So that'd be particularly if there's something where there are moving parts like engines or anything like that, where there's parts that move, it needs to withstand pulling. Bending strength, so we have to bend without breaking and cracking. Shear strength, which is to be able to withstand sliding forces in a parallel plane. Now, the best example for that is a pair of scissors, really, because they shear past one each, so they just pass past one another. Torsional strength is being able to withstand twisting. Then you got hardness. Now, hardness, it says here, is resistance to abrasive wear. There's two kinds of hardness. It's abrasive wear and indentation. Because remember, there are two tests to that. There's the abrasive test where you run a file or some glass paper across it, or you do the dot punch test. Toughness, which is the sudden impact, and it tends to be people get hardness and toughness mixed around. So toughness is that sudden impact, whereas hardness is able to withstand that indentation. Plasticity is able to for a shape to be deformed and then return back to its original shape. Ductility is the ability to be stretched without cracking, and then malleability is to be able to deform by compression without cracking. So that would be like hitting it with a hammer. So malleability and ductility are quite similar. The test is the same for those. The test for that is where you have like a piece of material in a vise and you bend it, and if the cracks appear on the inside or the outside of the bend, depends on whether it's ductile or malleable. And then elasticity is kind of similar to plasticity in a way, but it's able to return to its original shape after being deformed. So those are the mechanical properties. The physical properties are essentially things like how well can electricity pass through it. So if it can pass through well, then it's a conductor. If it can't pass through, then it's an insulator. Same with heat, so thermal conductor and insulator. So thermal expansion is how well do materials expand when heat is applied. Now there are instances where the properties are used intentionally. So things like on railway tracks. Now obviously this is to do with metals, not plastics, but um, railway tracks are intentionally built with a gap in between the joins because when it heats up in the summer and it's being used, it expands. And if you didn't do that, the tracks would bow and there would be an accident. So opaque, translucent, and transparent are the abilities for how well does light pass through it. So opaque being it doesn't at all, translucent being it passes through and it kind of blurs a little bit, and then transparent being that light just flows straight through it, not a problem. Density is to do with the mass of the material. Fusibility is how well does it convert from a solid to a liquid. So when you heat it up, how well does it can it be used as a liquid to be formed into something else? Magnetism um, is how magnetic something is. Now, obviously, again, this doesn't apply to plastics. And then corrosion and degradation resistance. So this is how well does it withstand things like chemicals or water or anything like that. Particularly with plastic products, if something is going to say contain bleach, if it's like a bleach bottle or anything like that, obviously it needs to withstand chemical corrosion. Otherwise, it's not going to contain the thing you want to actually physically contain it. So we've covered those before in the metals video. It will also be on the timbers video that's coming out as well. These properties, apart from like magnetism, which obviously only applies to metals, um, all of these properties, mechanical and physical, can apply to any material. So it could be timbers, it could be polymers, it could be metals, it could be papers and card, it could be smart materials. But essentially, whatever the product needs to do, you need to look at those kind of properties you have and see how suitable are they for what you want to do. Okay. So now that we've sort of gone over the generic bit of the properties of it, we'll look a bit more into the metal side of things. Now, obviously, we know plastics come from crude oil. They are derived a little bit from things like natural organic materials like coal and gas as well, but for the main part, it's crude oil. Now, obviously, that does have quite a negative effect on the environment. For the main part, there's huge amounts of drilling, particularly in the ocean now, and so only in certain parts of the world because it's a finite resource and we're running out. But there is also the fracking process which happens, which helps release gas, which is quite a controversial idea because what will happen is that you basically send high pressure water and air to break the ground, essentially like a little air explosion, to try and break the ground to release the gas that can then go into the pipe and come up and be stored. Now, the reason why that is controversial is because one, um, you don't know what damage you're doing around the ground. So obviously there are structures above the ground, so it may be over time you're going to do some serious damage to um, any structures that are above where you are fracking. You also may be damaging any wildlife that happen to live underground. And there's also the fact that you won't be able to harness or grab every single bit of gas because it's gas, so it's quite hard to actually physically contain. So once you like do an explosion to get it, there will be gas that is released naturally anyway. So it is a little bit controversial, but it's been used quite a bit. So we've just talked about why it's controversial and why it's used in England as well. Okay, so at the start of the video, I said there were 4 types of polymers. Now that's a bit of a cheat, really, because originally there's 3 main kinds that people talk about. So there's thermoplastics, thermosetting plastics, and elastomers. So we start with thermosetting ones. These are the ones that can't be recycled, and the way to remember that is they're thermosets, so they set in place once they've been molded. And the reason why they can't be recycled, so if I move my mouse over, you see what you've got. Ooh, is these rigid crosslinks. So essentially what happens once you've formed it, those rigid crosslinks set in place, which don't let the fibres then move around so you can't heat it up and recycle them again. Whereas that's kind of the exact opposite of thermoplastics. Because there are no rigid crosslinks, the fibres are all sort of going across from each other, it means that you can recycle it plenty of times. Now, obviously, there's a limit. If you keep recycling something over and over and over and over again, eventually it'll sort of wear down. But then what they tend to do is mix in some new thermoplastics or even some biodegradable plastics in with old thermoplastics to sort of keep the process going a bit. And then you've got elastomers, which essentially have good elasticity. So remember, elasticity is the ability to like deformed and return back to its original shape. They can be either thermoplastics or thermosetting plastics. They could be either or. So examples of thermoplastics. Now, there's no real exciting way really of sort of going over the factual bits you just need to know. There are quite a lot of plastics in the world. You're not expected to know every single one. Like with the metals, the best thing to do really is to remember a few key ones. So if you don't know in an exam, you sort of throw them out. So in the metals one we talked about, if in doubt, stainless steel is quite a widely used one. Aluminium is quite a widely used one. So if in doubt and you're not sure, whack stainless steel in there, whack aluminium, and there's a good chance you can sort of fluke your way into an answer. The same sort of policy applies with plastics, really. The most common ones, really, I would say that you'd use are things like LDPE, HDPE, polypropylene, and ABS. Those are sort of the 4 go-to ones. It's important to understand, or at least cover all of them so you're aware of them. But yeah, those are the 4 ones that if I didn't know, I would sort of throw those out. So low density polyethylene is typically used for things like carrier bags and cling film and those sorts of things. It's very tough, good chemical resistance, and it can be calendared and stretched to be nice and thin. High density polyethylene is good for like containers and also really hard wearing and tough. So you fit perfect for like things like children's toys. Polypropylene, mainly used for things like your Tupperware boxes that you've probably got in your house that don't have lids to them. Um, High impact polystyrene hips. Um, Used a lot in like yogurt pots and single use like little plastic cups and things. You probably know those hips from the vacuum format in college or school. Is the most common use you have for that where you are. ABS is extremely tough and it got very, very good heat resistance, and it's used for pretty much anything that's got like a hard case, and things like your TV remotes, your phone casings, um, soap dispensers on the wall. Now you've got all the hand sanitizer dispensers, those sorts of things. Those are all like really, really hard wearing ones. The other ones, we'll mention them just because they're important. Now, this one here, PMMA, um, oh, I should have said by the way as well, you're not expected to know the full chemical name for them. You are allowed to say the abbreviation in the exam. And in fact, I would recommend it because if you try and spell it and you spell it wrong, there's a chance you won't get the mark. So, yeah, better off sticking with the abbreviations. This actually is the full technical name for acrylic, which obviously is um, the most common used plastic you have in colleges and schools because obviously that's what you use in the laser cutter and those sorts of things. Nylon is very good, very tough, very corrosion resistant. Um, so that's using things like bearings and gears because it can withstand a huge amount of wear on it. Then you got PVC, excuse me, and UPVC. So UPVC is basically at home, all your window frames, your gutters, external doors. You've got those like plastic doors at your front or back door. That's what that is. And then PVC is essentially like anything like cable, housings, house pipes, medical grade tubing, imitation leather, anything like that. You do need to be careful with UPVC and PVC because there are some processes you can't use with it because the C in it stands for chlorine. Basically means that that's why you can't laser cut PVC because if you laser cut it, the gas that is released is actually chlorine gas, which obviously is very, very toxic. So you just need to be careful with those two materials. So elastomers, so these are the ones that you can deform and they'll return back to their original shape. So you got natural rubber. So this is typically used in things like the automotive industry. So things like tires, also things like footwear, and also balloons. So it's got really good tensile strength, which is why it's so good in the automotive industry because it can withstand a huge amount of pulling. Good hardness. It's good cold resistance, so it's good. It can withstand extreme heats quite well. Butadiene rubber, which is typically used car tires, shoe soles, hoses, that sort of thing. Again, very good wear resistance against friction, very tough, good electrical insulator. Neoprene, for the most part, if anyone does anything like surfing, windsurfing, scuba diving, your wetsuits are used by neoprene. There's also in secondary school, if you've ever had those pencil cases that had like the sort of wetsuity material, that was always neoprene as well, and the fabric laptop cases that you get. And then silicone, most commonly really used in things like cooking accessories, so like ice cube trays, bakeware and molds. If you ever watched like the Great British Bake Off, and they have like molds where they're making like chocolate shapes to put like decorate their cake and stuff, that's silicone because you can put it in the freezer and it's good at low. It still stays flexible at low temperatures, whereas other ones, once it gets low temperature, they tend to get a bit brittle, whereas silicone doesn't. So then thermosetting plastics. So these are the ones that then can't be recycled. So things like urea formaldehyde. So they're used a lot for electrical fittings, mainly because they've got very, very good heat resistance and they're electrical insulator. So that's basically all your plug sockets are made from urea formaldehyde. Because if you've ever had something plugged in and you go to unplug it and the plug is quite warm, if it had been another plastic, the odds are it would have started to deform and essentially melt a little bit. Melamine formaldehyde, mainly used for things like decorative laminates. So in your kitchen, unless you're incredibly posh or rich, your kitchen counters are probably melamine formaldehyde. Typically, they're meant to look like marble and that sort of thing. But yeah, normally you'll have like a sheet of 20 ml MDF or whatever you have, and then you'll have melamine formaldehyde cover over the top. It's incredibly hard, incredibly tough, good heat resistance, good food safe, so it won't contaminate your food. They also use it for like plastic, like picnic wear, like bowls and plates and those sorts of things. Polyester resin is mainly used in the layup process. So if you've not watched one of the videos on that yet, so the layup process is essentially if you're doing things like carbon fiber or fiberglassing, where you have the sheets of the fibers, you are adding the resin, so it's essentially like the glue sort of thing. So you're brushing it into it, and you keep doing more and more layers, and you'll brush the resin into it, and you'll roll it into a mold, and that's how you'll get things like boat hulls, F1 cars, like or any like complex car parts, particularly in like racing cars, that sort of thing. Then epoxy resins used a lot in like adhesives because it's a very strong glue. You may have seen or used like that's something like araldite or two-part epoxy, where you have the glue that's like a syringe, but it's two syringes next to each other because you have the hardener and the resin. You also do have the casting resins that we see a lot on social media, where people make like the river tables where they have two bits of wood and they have the resin and a dye and they pour it in. It looks very nice, but it is terrible for the environment. Okay, so those were sort of the three original groupings of polymers. I did say there's a fourth one, which we'll come on to in a couple of minutes. So we said additives. Now, with plastics, for the most part, they're what you call self-finishing. So typically you don't need to paint them. You can do if you wish to, but really the benefit of using polymers is you don't need to. They're also inert, so they're not susceptible to fungal or insect attack, but you can still change the properties. Like with metals, you can alloy to improve the properties. You can add additives to plastics to improve the properties as well. So things like fillers will reduce the weight and the cost. So essentially, it's kind of bulking it out. So if you think of it like orange squash, and you keep just adding water to it, and it'll go further and further. Obviously, you're not adding water to fillers. Typically, it's stuff like chalk and sawdust and that sort of thing. But it sort of bulks it out, so you're wasting less. Flame retardants reduce the risk of combustion. So combustion is where if it's near or like exposed to extreme heat, not necessarily just flame, but how likely is it to go up in flames? So that's particularly important, obviously, if it's near like electrical usage where it does get quite hot. Plasticizers will increase the flow. Now, with that, what it means is essentially its actual ability to like pour the liquid plastic. So particularly in processes like injection molding or extrusion, where you have to molten plastic to push into a mold or a die. If some plastics you try and pour them, it's essentially like trying to pour like honey or like treacle or something like that. So if you add plasticizers to it, it makes it flow. It's a lot easier to pour it in or like force it in. Stabilizers reduce degradation from UV. So this is particularly important if you have any plastic products that are going outside, like plastic garden furniture or children's toys or anything like that. Because what UV light does to plastics is it will make the colour fade, and it will also make it more brittle, which is why if you have plastic furniture for quite a long time, eventually it sort of starts to break apart and you sit on it one day and it snaps and you fall down. So stabilizer will prevent that from happening or slow it down from happening. Pigments simply just change the colour. So pigments are what give you your skin colour. Pigments what gives you clothes colour. If, like cooking, if you add pigments to cakes, it changes the colour of it. So pigments, you just add these to get different colours. Anti-static reduce the static build-up because plastics are generally quite good electrical insulators. So it actually attracts a very fine layer of dust, which is why you get all this staticky feeling to it. So anti-static actually attracts a very fine layer of moisture to the surface that stops that from happening. And then biobatch will allow polymers to biodegrade over time. So rather than sitting on a landfill, it'll let you degrade, and you can get things that will allow it to degrade over with oxidegradation, hydrodegradation, UV degradation. It depends what the thing is that you're going to do. So with these additives, I should have said at the start, really, is you can add these in during the manufacturing process. So say if you're injection molding children's toys, if you want to change the colour, literally as the plastic has like been melted down, you would just add the additives to it. So you'd add the pigments to it at that time, and it would change the colour. So these can all be added in during the manufacturing process. So the recycling table, hopefully you've seen this before. So 1 to 7, 1 being really easy to recycle, 7 being it's not going to be recycled. Please don't refer to the recycling logo as that it is the Mobius loop. You'll find all plastic products now, as a requirement, have to have these molded into, typically into the inside lid or the bottom of a product. So all your drinking bottles will have PETs that have the one molded into it. The reason they're there is two reasons really. One is so you as a consumer know whether it can be recycled or not, and the second one being that it helps people at the sorting plants to be able to like judge which ones can be recycled, which can't, and they can separate them because you don't want to mix plastics together when you're recycling them, otherwise it kind of comes a bit useless. But typically speaking, things like plastic bottles are really easy to recycle because they're PET, although it's worth pointing out the lid is actually a different material, and all the way down to 6 and 7. So polystyrene is horrendously bad for the environment. So if you ever go to like the kebab shop and you get that polystyrene burger box where you get your chips in or your burger or whatever, and those are terrible for the environment. Along with like your polystyrene packing peanuts that you get sometimes when you get things delivered, and it has those little polystyrene things to hold it in place. And then other can be used as like basically a mix of any other plastics that are mixed together and then can't be recycled. So typically things like toothbrushes, which are made up of 3 different plastics, so they essentially just get chucked in a landfill because you can't separate them. So we talked at the start about fracking. So obviously plastics are pretty much all crude oil, but there is a little bit of other things in there as well. But plastics come from oil, obviously, which means that they're finite, they're non-renewable. At some point in our lifetime, they're going to run out. We can recycle thermoplastics, however, at some point they sort of wear out. So it's kind of left us with the need to look for a plan B. Thankfully, there's some very smart people who have started to do that with your renewable plastics. So essentially, what you can do is you can make biopolymers, which are derived from plant or animal extracts. So if they can produce hydrocarbon chains, it means that you can produce polymers from them. Okay, so it does take quite a lot of energy to do it. It's quite difficult to do. Well, difficult is wrong. Time consuming to do. Time consuming and expensive to do. So I've got a couple at the bottom there. We are going to go over them again in more detail on the next slide, so I won't bother talking about them too much. But generally, things like corn plant, potatoes, grown from bacteria, those sort of things. So you've got 2 general groups. You've got the natural and the synthetic. So the naturals are the ones that come from plant and animal extracts easily. The synthetic ones are the ones that are essentially grown in labs, really. So again, you maybe not expected to know every single one. There's some the key ones really that are used. So things like potato pack is used quite a lot. That's used nowadays if you get, say, like a ready meal that comes with like a knife and a fork. Sometimes now that's starting to be used as like potato pack quite a bit. You can also get picnic, like disposable picnic utensils and plates and those sorts of things. So that's potato pack because it's literally just potato starch, and it's single use, so you can chuck it and it will dissolve and degrade quite easily. Um, PLA. So if anyone's into their 3D printing, PLA is one of the most common materials used now in 3D printing, and that is made pictures from corn kernels or like sugarcane, and it's fermented and it's sort of synthesized and grown in a lab. The main problem you have with biodegradable polymers is that it still takes quite a long time to produce quite a lot of it, um, and that they are still relatively expensive to do. But what you can do, as we talked at the start a little bit with thermoplastics, is that you can mix some biodegradable polymers with thermoplastics um, to sort of stretch it, make it go further. So particularly things like biopol is used quite a lot, where you'll add that to thermoplastics. It'll help it break down, but also it means you've just got more plastics to use. Okay, so on there you've got 8 products. Take a second, can you just pause the video? Can you write down what material you think it is made from, and then what group is it, and then can you think about how it would be made? Once you're done, unpause the video and we'll go through it. Okay, so the first one, plastic bottle, will be PET, which is 1 in the recycling table. So that'll be blow molded. The easy way to know how things have been blow molded is if you turn it upside down and you see that little nipple shaped thing at the bottom. That's typically where the paraffin has been pinched together, and basically where the plastic has been pinched together with the mold and it has been blown through it. The plug is urea formaldehyde, and that we're dealing with compression molding because you're making loads of them, and it's literally just you have your blanks of plastic and push through nice and easily. The power drill is ABS because it is very hard wearing. Obviously, being a tool that's going to be in a workshop needs to withstand a huge amount of wear and tear. Because it's relatively complex, it's injection molded. Next, you got polystyrene, which is the yogurt part which will be vacuum formed. You could also have something like polypropylene or HIPS as well, would have been acceptable. Then you've got anything like guttering or window frames would be UPVC, which would be extruded. So extruded is just where you have everything like one long continuous sort of shape. So this, I don't know what you would really call this, just sort of like a bent piece of plastic. So that's acrylic and something on line bending, which you've probably used in like year 7 or year 8 if you took design technology of any kind in college or secondary school. Carrier bags will be LDPE and done with calendaring because it lets you stretch and pull and like compress, and then you pull it out and you've got a very nice thin layer that you can add graphics to make your bags. And then you got HDPE for your kayak, which will be rotational molded, because then you can make it a nice hollow shape and it can have no joins, because if you have a join in your boat and then suddenly you spring a leak and you drown. Okay, so that is the main bit of polymers. We're going to have a look at some questions. So you've got 8 questions on the screen. Can you pause the video, have a go answering them, and then I'll put the answers on the screen for you as well. Okay, answers on the screen. If you've got any questions about this topic at all, please do send me a message either via email or Teams and I'll get back to you.